Thank you, Lara. So before we dive deep into what quench monitoring is all about, let me just make sure that everybody's fully clear on what I refer to by the technique of through process temperature profiling. In heat treatment, obviously measuring or monitoring your product temperature is very critical to the heat treat step that you're performing. If you don't know what that temperature is, you haven't got the control of your process, which could affect the quality of your product. In order to monitor the product temperature, we really need the temperature of the product, not necessarily on the surface, but maybe in the core of the product, and not just at unique points in the furnace, but all the way through the furnace. So in order to achieve that, you can use a technique referred to as through process temperature profiling, whereby a monitoring unit or a data logger travels through the furnace, measuring the product temperature with thermocouples. If you've got a number of channels, you can place those thermocouples at different positions on the product, maybe of different thermal mass, or different parts of products in different locations in the furnace. So you can get a full picture of what the furnace heat process is actually providing. Obviously, if the data logger travels through the furnace, we need to protect it. So we would use what we refer to as a thermal barrier, or it's a enclosure that protects the data logger from the hostile environment of the furnace. In most cases, that's going to be temperature. But today, obviously, if we're dealing with quenching, it may need to protect against other things like oil, like water, like salt, or high pressure gas. And we're going to talk about the design of those barriers to provide that protection. So the system travels through the furnace and it measures what we refer to as the thermal profile. And that's really the thermal fingerprint of your product's heating in the furnace. And that is critical to you understanding whether or not you have the conditions you need for the quality of product that you want to produce. But the question is monitoring the heating cycle all we need to focus on? And as you can elude from this presentation today, we're going to focus on what happens after the furnace in terms of the quench, which in my view is just as critical as the furnace itself, but is often ignored. Okay, so just to illustrate why monitoring the quench is important, here we have some examples of typical heat treatment applications that people may wish to monitor. There are 9 applications on the slide, but you'll notice that the bottom 4, each one of them involves not only the heat treatment furnace or the heating of the product, but a subsequent quenching step where the product is rapidly cooled from the set point temperature achieved in the furnace to a nominal cool temperature under controlled conditions. And each one of those applications are going to use a different quench technique or a quench media to achieve that cooling step. So it shows you how often quenching is part of the heat treatment process and therefore how critical it can be. Before we go much further, it's probably best if we just make sure that we fully understand what quenching means or what the actual technology involves or why we perform it. I know there's been other presentations that GTS have put on around the theory of quenching, but just to focus on this just for a few seconds. Quenching is obviously the rapid cooling of the workpiece or the product in a media, and that's typically water, oil, or air, to obtain certain critical metallurgical properties in the metal itself, and that involves the core of the product. So when we talk about quenching, we need to ensure that the quench or the rate of cooling, the quench rate, is controlled. Each of the media that we're going to look at today, from gas through to water, will provide a unique quench rate or a series of rates that you want to use for your application. So it's important that you match the quenching technology or the quench media to the type of heat treatment process you're doing. And we'll look at the examples that I referred to before. So we know that quenching is critical because it's pointless achieving the metallurgical state of your product in the furnace and then losing those properties by the slow cooling of the product. Often we need to maintain or freeze those metallurgical characteristics within the metal through this quenching step. So what are the key reasons why we should monitor the quench? All right, we need to understand, as we do in a heat treat furnace, that the product may heat up at different rates, depending on where it's positioned or its thermal mass or the makeup of different thermal masses in a particular product. If that applies to the heating step, it will also apply to the cooling step. So we need to understand whether all of our product is cooling at the same rate, because if it isn't, firstly, we may not get the metallurgical properties of the product we're trying to achieve, which is critical to its physical quality or its performance when it's being used as that product. But possibly more importantly also is that if we've got differential cooling rates within a product, that can lead to distortion and warpage of the product, which obviously is not a favorable observation to have within the process, because you don't want to distort the shape or the form or the appearance of the product, because it then probably won't do the function it's designed to do. And in worst case scenarios, we don't want to damage the material, where excessive cooling can cause what they've referred to as quench cracks, where the cooling is so severe, so rapid, that different thermal masses of product will heat at different or cool at different rates. It will cause cracking within the structure of the product. Obviously, with any process, you want to monitor and optimize that process, but you also want to make sure that it's running at the optimal conditions over a period of time. So you need a means by which you can show that your process is working correctly, and then have something as a template to compare against as you go forward in production. So we need to optimize the characteristics of the quenching. It may be the choice of the quench media, but within that, if you've chosen, say, for instance, oil or water, it may be then determining the right parameters for that material to work effectively. The temperature, the agitation, the type of material that you're using, as we'll describe or look at in more detail later. And obviously with any process, problems can occur. And with quench media, the media itself, its performance, particularly for instance, oil, can degrade with time. So you need to have a means by which you can monitor whether or not that material is still working at its optimum level. Knowing when those conditions aren't achieved allows you then to make the decision to maybe change the material or clean the material. And you can make very key, important decisions based on hard facts rather than guessing or basically assuming you need to change the oil based on historical events. As I described earlier with introducing through process temperature monitoring, at the core of the monitoring system, you have a monitoring device, which is often referred to as a data logger. This is basically a sophisticated piece of electronics which allows you to accurately measure, using a thermocouple attached to the product, the temperature where that thermocouple is positioned, whether it's on the surface of the product or in the core of the product, or maybe even in the environment of the furnace. So you can control what you're actually physically measuring if you know where that thermocouple is placed. For quench monitoring, though, it's important we consider some important design criteria for the data logger itself, because you can't necessarily use a standard off-the-shelf data logger for those very harsh monitoring requirements, where you're going from maybe a furnace that's typically at 900 degrees into a oil quench that's at just below 100 degrees into an oil tank. The logger has to be robust, it has to be physically strong, but it also has to be able to protect from what we refer to as ingress of the liquid or the solution or the media that you're using for the quench. For the typical data loggers we recommend for quench monitoring, you would be looking for what we refer to in terms of a specification as IP67. IP stands for ingress protection, and it's basically a scientific standard or a certification mark that states that you have a high level of protection against water ingress into the product, and that would also involve oil and salt. So we need to make sure that we have a very well protected data logger from the media that we're wanting to monitor or transfer into. The other important thing that people often maybe overlook is that the quench process, as we'll see in a few minutes, is very short. It's typically only a couple of minutes at most. Now, this is 2 minutes in a process that might be 4 or 5 hours long. So you need a data logger that's able to measure at very rapid rates to be able to give you the resolution you need to monitor that rapid temperature change in the quench. But at the same time, you need a memory in the logger to allow you to collect up to maybe 6 hours of data if you're sampling or recording data every half a second, maybe up to 20 thermocouples. Okay. So that's some of the key requirements of the data logger, in addition to some of the other things you can see listed on the slide, which are requirements for general heat treat monitoring apparatus. Let's then look at our first example, our first heat treatment application. Now, I'm sure many of you will recognize on this slide now a very, very well-known temperature profile for what we refer to as the T6 process for heat treating or solution heat treating of aluminium. The process involves heating the material in a furnace between 450 to 500 degrees for maybe 3 or 4 hours, and then rapidly cooling that material in what we refer to as a water quench or a water tank. Now, the reason we're quenching in this particular application is because we want to ensure that the alloy elements precipitate out of solution within the aluminium, which is going to give the physical properties of the aluminium, give it its strength and its ductility for its end use. The quench process is then subsequently followed generally by an artificial aging process where the product is heated typically at approximately 200 degrees for, again, a few hours duration. So we've got the solution treatment, the quench, and then the age hardening. So what we would like to do is to be able to monitor each one of those separate phases of the heat treatment process. So how do we go?
Process, for example, what were the challenges that you guys went into when you were trying to do this type of profiling or this type of quench specifically?
Okay, so Laura, it's a very good question. Obviously, the challenges for this particular process is firstly that we have to provide the thermal protection in the first part of the process, which is the furnace, typically up to 500 degrees for a number of hours. And when we're talking about 3, 4, 5 hours, you need a thermal barrier with some significant insulative behavior to give you the protection of the data logger. After that, obviously, we're then going to take a hot system and then plunge it into water. Now, obviously, if you are concerned about warping and damage of your product through rapid cooling, the same thing applies to maybe the monitoring device. So we need to make sure it's strong enough to withstand that. But then after the quench, we obviously need to provide the waterproof protection, as I said before, the IP67. So the barrier needs to make sure that the data logger doesn't get filled with water, because that's obviously not a good thing. Electronics and water, oil and salt do not mix very well. So you need to protect your data logger very significantly. And then we need to move on to the age hardening. So even after the furnace and the quench, we need to add further protection. So the crux of the problem is solved by the system you can see on the slide now. What we have is the data logger here at the front, which is located in the center of the thermal barrier. You can see the top of the slide here. Now, the monitoring system sits in the product basket with, in this case, our example here is with alloy wheels. And the thermocouples are then positioned at different locations on the product or different products within that basket. So this product basket travels through the process as a single entity. So everything is contained, it's safe, there's no trailing thermocouples, there's nothing that can get tangled or distorted or damaged. Now, the question is, what's happening in this thermal barrier? How do we get the thermal protection to achieve 500 degrees for 4 or 5 hours? What we use is a very simple approach, but an effective approach using the phase change of water. So the data logger is contained inside a water tank. Now, we all know that water will absorb heat fairly effectively and its temperature will rise to 100 degrees and then it will boil. Once it gets to that boiling point, the temperature is then maintained as the water boils and steam is released. But the temperature will be retained at that temperature of 100 degrees for as long as there is more water in the tank. So if we develop a system where the tank has enough capacity to last the duration of the furnace, we will be able to maintain the temperature of the data logger at 100 degrees. Now, the data logger is capable of operating up to 110 degrees, so it's working very safely in that situation. At the top here, you've got the barrier, but there's a cutout diagram here or a photograph showing you the inner core. This is the water tank. And around that water tank, there's a structural encasement. And there is also insulation blanket, which slows down the absorption of heat by that water tank. Now, interestingly, because the logger is in the center of the tank, it's in a tray which is completely sealed. So any moisture or any water in the quench tank when it's submersed can't get to the data logger and cause any damage. All right. Now, the interesting thing is that this is the phase change of the water. So we need to make sure that there's enough water in the tank to maintain the temperature of the logger below 100 degrees. So we can have different size tanks to suit the duration of your process. Excuse me. Now, the important thing is, obviously, the water in this tank will evaporate off during the furnace, but when it goes into the quench, it will actually replenish itself. So it then it's a bit like a battery. It will recharge itself with water from the quench, and it will then give you subsequent protection for the age hardening process that follows the quench. So here we have an example of the typical profile that you get from a T6 process showing the quench. Now, the quench is quite a rapid temperature drop because water is one of the most effective quenching medias that you can use. And you have to be a little bit careful because it's one that will most likely cause distortion, and particularly for aluminium, where you're working very close to the liquidus of the aluminium in the first place in the solution heat treat furnace. And the fact that aluminium has twice the expansion coefficient of steel, so it's likely to expand and contract very quickly with temperature change. So you have to be a little bit careful that you are controlling that temperature so you don't end up with the problems of warpage or expansion and contraction, which causes cracks. Because at the end of the day, as we've said before, you don't want to deform the shape and the form of the product through that rapid cooling process. But at the same time, you want to ensure that you're cooling rapidly enough so that you maintain the precipitation or the metallurgical characteristics at the core of the product that you've achieved in the furnace. You're freezing that metallurgical state in the product itself. How, you may ask the question, how can we go about then controlling the cooling rate with water? Now, there's some very clever chemistry you can apply to the water quench in this type of application. One of the most common ones is using ethylene glycol as an additive to the water. Now, what this does is it modifies the characteristics of the water, and in many respects, it creates almost a pseudo oil, which will, and the cooling characteristics for a glycol mix is very similar to an oil, as we'll see later on in some of the slides. When you add this material to the water, it creates a film on the outside of the product itself as it goes into the quench tank, and it will reduce the rate of temperature change initially before that is sort of evaporated off, a bit like the characteristics of oil, as we'll see. But the concentration of the glycol and the mixing of that will affect the rate of change. So you have some control over the characteristics, but you would monitor this using the same system as we described for the water quench.
Would the ethylene glycol have an impact on the thermal barrier at, I mean, short term or long term, maybe?
Not really, as long as you obviously there's a challenge associated with actually cleaning things down. You may need to change the insulative blanket more often, because once it gets impregnated, the actual glycol gets impregnated into that material, it may compromise the performance a little bit, but you may be able to wash some of that off. I don't think it's quite as bad as oil, as I'll describe later, but you have to maybe be a little bit careful.
Perfect, thank you.